Okay, so as we begin our adventure with remotely delivered labs, we're in some respects fortunate that our first attempt is going to be with special relativity. We're fortunate because even if we were conducting this lab together in PS19, there are very few relativistic effects that we can directly observe with the equipment we have for the simple fact that we're slow, right? And a lot of the special relativity effects, as we've observed in our lectures, just aren't very noticeable uh, until objects are traveling at a significant fraction of the speed of light. So, what we'll do today is more of a workshop type model where I will do more lecturing than I normally do, and then I'll give you a set of problems with answers, and it will be up to you and your lab mates to come up with solutions um, outlining uh, how to do the problems. So, one of the first things that I wanted to address are some of the classical uh, paradoxes of special relativity. So, um, so these are actually kind of fun, um, and I hope that you enjoy them. So let's get started. So the first one I want to talk about is the so-called twin paradox. For the purposes of this, let's assume that I am one half of a set of twins. And as I start every day with a Milky Way candy bar, you probably are somewhat aware that uh, I know very little about biology. Um, and so I'm a little bit naive, but a lot of what I know about biology comes from Saturday morning cartoons, and it seems uh, that in every set of twins, one is born evil and one is born good. Um, Now, for the sake of argument, uh, today and pretty much all semester, many would argue, I will be playing the role of evil Mark. Um, Now, probably this is uh, uh, failure to plan on my parents' part, right? If you name one of your children evil Mark and the other twin good Mark, I think you're setting yourself up for disaster. But that's beside the point. So in today's uh, discussion of this paradox, uh, I have upset good Mark. He is very easily offended, and and so he is encouraging me to uh, to leave, and so I will. And so um, I have my little spaceship, which I can't draw spaceships, so it looks a lot like a space shark. But I'm going to travel away from Earth at about zero point 0.6 C. Hopefully the setup makes sense here. Now, here's the fun part. I have apparently really upset Goodmark um, this time, and he is while teaching remotely, I've learned a new word. Um, he is using his smartphone. I think I'm saying that correctly. Smartphone to take a selfie. Is that what they're called? Um, of himself giving me the one fingered salute. Um, and he's gonna send one of those pictures uh, let's say I he I he sends one every 10 minutes. Um, the question then becomes, do I receive them every 10 minutes? Well, no, I don't, right? In fact, I don't receive them every 10 minutes because I I because I am traveling away from the source, right? And so each successive message has a little further to travel than the last one did. And so um, I'm not using real math here, um, but let's say he sends them every 10 minutes, and let's say I receive them every 12 minutes. Well, how much does he look like he's aged picture to picture? He looks like he's aged, uh, well, 10 minutes, right? We're twins, and so we can see that how much the other is aged. Uh, how much have I aged between the receipt of every successive picture? Well, I've aged 12 minutes. And so, um, he doesn't seem to be aging as fast as me. Uh, maybe there's something to be said for living a, a good and honest life. Um, you might notice that there doesn't appear to be a lot of space for Milky Way candy bars on the Space Shark. So obviously I can't stay out there forever, and so I'm going to uh, take a selfie of my own. I'm really proud that I've learned that word. Uh, and I'm going to take a drop of water and I'm going to paint a little tear on my cheek, uh, look sad and say I'm sorry. I'm not really sorry. Um, and I'm going to send one back to Earth every 10 minutes. But for the same reason, each successive image will have further to travel than the last. Goodmark doesn't receive them every 10 minutes, even though I'm sending them every 10 minutes. He receives them, I think we said 12 minutes for me. He also sees that I am aging slower than him. So thankfully there is no benefit to living a good and honest life. We can set that aside. Um, we both see the other is aging slower. Well, that's consistent with what we were talking about in lecture um, earlier this week. I'm losing track of time at this point. Um, at some point, because he's Goodmark, he's um, he's easily fooled by my pictures pretending to be sorry, and so he says, "Okay, you can turn around and come back." And so I do, and and so now the question becomes, when we're reunited, well, we both saw the other one aging slower than we were aging. Who was right? Were neither of us right? That's our qualitative pass at this. And I would like to take a, a slightly more quantitative pass at this problem. And so I have uh, drawn on graph paper um, kind of the trip. My colorblind eyes have difficulty seeing what's going on here, and so I've done this more carefully in I I've drawn what's called a space-time graph, um, and I've drawn this in uh, on my tablet, and I want to try and make clear what we've done here. So uh, I'm largely going to tell this story from the standpoint of Goodmark, who stayed at home. And so I'm going to only worry about one direction. Um, so as we increase along x, we're going further away from Earth, and as we decrease in x, we're coming back towards Earth. So this, and by the way, on the vertical axis, I've plotted c times t, and I know that probably seems like a weird thing to do, right? Um, you can think of this as our stand-in for the time axis, right? It's going to have units of meters, right? Um, and I'll justify why we're doing that towards the end of this talk. But um, let's look at what's happening here. So what we have is Evil Mark leaves Earth and travels out, and then and I'm going to do this in terms of years just for the sake of simplicity. Travels out for 5 years, gets the signal that it's okay to turn around and come back, and so does, and then comes back, and always is traveling at 0.6 c. So this blue represents what Evil Mark is doing, right? Over time, traveling away from Earth, right? This is the away from, the horizontal represents the away from Earth. And then after 5 years, gets the signal that it's okay to come home. And so 5 years later, makes it back to Earth for a total trip on stay at home Mark, right? So notice that stay at home Mark, in if I plot stay at home Mark, good Mark's distance from Earth, after 1 year, it's still 0. After 2 years, it's still 0. 3 years, it's still 0. 4 years, it's 0. 5, still 0. 6, 7, still 0. 8, 9, 10, still 0, right? Good Mark stayed at home, and so has an infinite slope on this space-time graph. But uh, good Mark, good Mark stayed at home. Evil Mark uh, has a speed uh, of 0.6 c, right? Which is uh, 3/5 of c. And so on this space-time graph, the slope should be 5/3. And so note that I've gone over 3 and up 1, 2, 3, 4, 5. Yay. And then coming back, obviously, the slope is the minus 5/3. So let's see what this does. So instead of signals every 10 minutes, I'm going to send signals once a year. And so first, I want to look at signals that good Mark is sending to evil Mark. So the first signal at year 0 is good Mark telling evil Mark to leave. That's not very good, right? Maybe good Mark and evil Mark, but good Mark kicks evil Mark off of planet Earth. That signal hits evil Mark at the origin, right? The year 1 signal, well, on this, if I'm plotting this in terms uh, of light years and light years, right? C times t, speed of light times 1 year would be 1 light year. Well, the slope of light on this graph, on this space-time graph, should be 1, right? The how many light years does light travel in 1 year? Well, 1. How many light years has light traveled in 2 years? 2. 3 and 3, right? 4 and 4. That makes sense. So The year one signal where Goodmark is flipping me off, right? Telling me he's still mad. Well, it leaves Earth at year one, right? Notice that this is all as far as Goodmark is concerned. And it intersects, right? This is where Evil Mark receives that signal. Yeah? Doesn't receive it instantly. It takes light time to travel. The year two signal, because Goodmark is just inherently good, I guess, is that he forgives me and I can come home, right? But again, I don't receive that straight away. I don't receive that uh, until the light signal reaches me. But at that point, I get that signal that it's okay to turn around and come home, and so I do. And so now let's look at more in full, right? So that, again, the year zero signal is when I left. The year one signal arrives, telling me that he's still mad. The year two signal tells me that it's okay to come home, and so I turn around. But at this point, there are all of these signals in between that I'm going to now run head on into, right? And so now I'm going to see them come at me in a hurry. And so the year three signal arrives right there, right? The year four signal arrives right here. The year five signal arrives right here. The year six signal arrives right there. The year seven signal arrives right there. The year eight signal arrives right there. The year 9 signal arrives right there, and then I get the year 10 signal right as I'm getting home. Now, what I want to point out is that um, there is definitely this shift in how often I receive signals, depending on whether I'm moving away or moving towards. And so now let's look at this response, right? So the total number of signals I received is 10, right? Hopefully you can see that. I'm not counting the year zero signal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10 signals while I was off Earth. The year zero one is the one that kicked me off Earth. Hopefully that's okay. And so what I so let's turn our attention now to the signals that I send back. Here we have to be careful because we have to think about what we mean by simultaneity. And so um, the first year of travel for me, right? Remember that we can look at the time dilation, and so if 1 year has passed for me, it looks like 0.8 years has passed back on Earth. And so I want to send a signal back. I think that's green, right? The green signal is me sending a signal back. But I want to send it when 1 year has passed on my ship. But 1 year has passed on my ship, that should be when the simultaneity signal arrives that 0.8 years has passed on Earth. And so um, the slope of is that pink, the ones that's attached to the little numbers, the 0.8, the 1.6. the slope of that should be 0.6, or minus 0.6, depending on which direction we're traveling. Um, so, uh, so simultaneous to 0.8 years having elapsed on Earth, um, while 1 year should have passed on the ship, according to me, right? That's it looks when I see that 0.8 years has passed for my brother on Earth, 1 year should have passed on my ship. And uh, so I'm going to send a signal back, and it's going to have a slope of -1. Why will it have a slope of -1? Well, it's traveling at the speed of light, right? And again, it's light years and light years. Well, if after 2 years, we should have a line of simultaneity of 1.6. Again, this slope uh, is 0.6. So this is when 2 years has passed on the ship. I'm going to send another signal back. This is when 3 years has passed on the ship. I'll send another signal back. Note that uh, so far this looks somewhat symmetric to what we saw on this set, right? Except that now things are about to get a little funny, because once I turn around, um, well, let's see, my year 4, right? 1, 2, 3, 4. Um, Still heads back with a slope of this -1. Doesn't get there until year 8 has passed on Earth. Now I'm running back through all of these simultaneity signals. So when 7.6 years has passed on Earth, um, that's when our 1, 2, 3, 4, 5 years has passed on the ship. And so I send another signal back. And then when 6 years has passed on the ship, I send another signal back. When 7 years has passed, I send another signal back. When 8 years has passed on the ship, I am just arriving home. And uh, and so I send this last signal. So note that only 8 years have passed on the ship as far as I'm concerned. And I can get my Milky Ways, right? So year 2, running low on Milky Ways. Year 3, I'm going to say I'm sorry. The thing that I want to point to is, so note that right now signals are arriving every 2 years for 8 years of the travel as far as Earth is concerned. And then the last 2 years of travel, they're receiving 2 signals per year from me. But that still turns out to, uh, well, 1/2 of a signal per year for 8 years is 4, plus 2 signals per year uh, for 2 years is 4 more signals. So 4 plus 4 is 8. Earth gets 8 signals from me, but while I was gone, I got 10 signals from Earth. And so when I return, I really will be younger than my stay-at-home twin. How could that be? Well, um, in part, what we have assumed is that this turnaround occurred instantly, and so there was an acceleration, right? It's not the special relativity frames break down if one of the frames is accelerated. Special relativity is special because there's no acceleration of the frame. The frame that didn't accelerate was the stay-at-home twin. So we can use the stay-at-home twins description, um, as one solid frame, but note we need two different frames for uh, for the traveling twin evil mark for me, right? And the trick is uh, is that notice this turnaround is where we went from these signals spaced out dramatically to these signals spaced out uh, very uh, very small amounts, right? The other thing that you can think of is, well, how am I going to explain only being gone for 8 years? Well, uh, I also don't think that the distance I traveled was as great as the distance uh, that Goodmark stayed at home thought it was, right? So not only do we have time dilation, we also have length contraction. So figure out uh, the who gets to be the proper frame, who gets to be the one measuring the proper length for for distance, and then that will help explain why I why I only think it took 8 years to travel round trip. So okay, that is our twin paradox. I also want to look at our pole vaulter and barn paradox. Um, this is another of our classic paradoxes. This time you are the person of interest, um, uh, for safety's sake, my safety mainly. Um, and you have taken up pole vaulting. The Olympics are next year now, the Summer Olympics. You have a whole year to get ready, um, and you are. Uh, why you're doing pole vaulting, I'm not sure, because if you can run that fast, you should be doing, the sprints or something. But you are late for pole vaulting practice, and so you are going to cut through your neighbor's barn. Um, your neighbor is sick of you doing this day after day after day, and so has decided uh, to to teach you a lesson. Doesn't want to hurt you. So here's your neighbor who suspiciously looks a lot like you. It's almost like a lazy person was drawing these things, and just copied and pasted and turned it in the other direction. Huh. Um, but your neighbor doesn't want to hurt you, just wants to scare you a little. And so here's the trick. They your neighbor has installed some automatic doors on the front and back of the barn that will instantly open and close. I know that that part makes this seem a little far fetched, but it's also probably a little far fetched that you're running 3/4 the speed of light. So suspension of disbelief a little bit here. Um, the uh, the trick here is uh, is that your pole vaulting pole is 15 meters, which is insanely long. That's um, way longer than I think they're supposed to be, but I wanted nice round numbers for us. And your neighbor's barn is only 10 meters. And so what's going to happen is your neighbor is going to see length contraction of your pole vaulting pole. And thankfully, it's going to be length contracted small enough that it's less than 10 meters, so it would fit in the barn. Your neighbor is going to, as soon as you're inside, close the doors and then instantly open them. Just scary a little, right? And so let's just double check that uh, that this is going to turn out okay, that your neighbor has thought this through. So according to your neighbor, uh, if your if your pole has a proper length of 15 meters, um, because you are moving so fast, it will be length contracted down to 9.9 meters, which will fit inside the 10-meter barn. Hooray, right? The barn is 10 meters. Your neighbor says that the pole is only 9.9 meters. No harm, no foul. The paradox here is when we consider this problem from your standpoint, because you are going to say, no, the pole really is 15 meters, but the barn is length contracted. So the barn isn't actually 10 meters, it's only 6.6 meters. And so here is our problem, right? Your neighbor is going to trap you inside the barn just for a moment, right? And then open the doors. But you think the barn is too short to hold the pole anyway. And so do you make it through safely? Well, you both have to agree on what happened, right? The qualitative level feel here of did you get smushed inside the barn? Um, you both have to agree on that, right? There is a truth in that. The how you didn't get smashed, you don't have to agree on, and that's what I want to explore again with one of these space-time graphs. So um, let's. This is trickier than the last one, right? Because we have uh, 4 events that we need to follow. Well, 2 events, but 4 things that we need to follow. We need to follow the front door of the barn, the back door of the barn. We need to follow the leading end of the pole and the trailing end of the pole. And so, first, let's look at this from your neighbor's perspective. So, here, the infinite slope belongs to the front door and the back door because your neighbor says they're not moving. Hopefully, that's okay. How far apart are they? Well, they're 10 meters apart. Yay? The other things that we need to worry about are the trailing end of the pole and the leading end of the pole, and your neighbor sees them coming towards him. In fact, uh, since your speed is 3/4 the speed of light, the slope should be 4/3. And notice that the slope here of both the leading end of the pole and the trailing end of the pole are both 4/3 here. And again, I'm using CT, the time axis. I'm plotting it in meters, right? Um, and and it just makes this graph a little easier to understand. Um, so what I want to do is I want to think about when your neighbor. So let's start the clock. T equals 0 when the front end of the pole passes through the front door, right? This first one is the front door. So we're starting the clock, t equals 0 meters. I know you love using meters to describe time, but CT is 0 meters when the leading end of the pole passes through the front door. Well, how long is it going to take before the leading end of the pole makes it to the back door? Well, that's actually a pretty easy problem, right? You have speed is equal to distance over time, so time is distance over speed. We know the distance is 10 meters, so the front end of the pole will make it to the back door. Um, I over I 0.75 I c is the speed, and so this gives me kind of a rough statement that the time when the leading end of the pole is going to make it to I to the back door will be about 13.2 meters over c, or C delta T is 13.2 meters, right? And so notice that, in fact, because I tried really hard to scale this, that really is occurring at about 13.2. I'm pretty proud of the way that drawing turned out. Let's look at the back. Let's look at the trailing end of the pole. Well, it was 9.9 meters behind, and so 9.9 meters over 0.75 C is going to take the same amount of time, right? So it was that far behind. It will also make it so that the trailing end of the pole enters the front door at the same time, right? Notice that that's yellow. This yellow line represents the time, 13.2 meters over C, when both the front end of the pole and the back end of the pole are inside the barn. And so your neighbor can slam the door shut and open it instantly and scared you a little, but you made it through okay. That wasn't the part we were worried about though, right? Let's look at this from your standpoint. From your standpoint, the front and back end of the pole are not moving relative to you, but the front and back door of the barn are racing towards you at 0.75 C. And so here we have the trailing end of the pole is now vertical on this CT, on this space-time diagram. And the leading end of the pole is also infinite slope because, again, neither of them are moving relative to you. So this one we just did is from your neighbor's perspective. This one's from your perspective. And this time, the trailing end of the pole and the leading end of the pole not moving. But the back or front door of the barn are racing towards you with that same slope, well, the negative of that slope, right? Over 3 up 4, right? Here, we'll go to the bottom. Over 3 up 1, 2, 3, 4, right? So we're okay with that. So this time, let's track the leading end of the pole and note that so we're going to, again, start the clock when the leading end of the pole passes through the front door, right? That's CT equals 0 meters. And I want to take note of when does the leading end of the pole make it to the back door? Well, the leading end of the pole makes it to the back door at, that looks a little under 9, right? In fact, we can calculate it. We already said that the barn itself was 6.6 meters. And so 6.6 meters over 0.75 C, it should take about 8.8 meters over C for the leading end of the pole to make it, or the back door to make it to the leading end of the pole, which is what you see here. Again, I'm really proud of how well scaled these are. If that's 10, that's 9. It's a little under 9, 8.8 meters over C. Let's look at the trailing end of the pole. Well, when does the trailing end of the pole make it to the front door? So the trailing end of the pole will make it through the front door not until here, right? So notice that that the other thing I needed to state is notice that this time the front end of the pole and the back end of the pole, they're 15 meters apart. Why 15 meters apart here? Well, because in your frame, the proper length of the pole is 15 meters, right? They were only 10 meters or 9.9 meters apart here because, according to your neighbor, the length of the pole is 9.9 meters. But in your frame, they're 15 meters apart. So now notice that the front door is going to make it all the way to the trailing end of the pole? Not until here. In fact, we can calculate that too. Delta x is this time, or sorry, delta t is this time delta x over v is 15 meters over the same 0.75 c. Well, this is a little easier mathematically. It's 20 meters over c, which again is right where these graphs predict. So note that this is a little weird, right? Because as far as you're concerned, uh, the uh, the front end of the pole is completely out before the uh, the trailing end of the pole has even entered. And so how could it be then that the neighbor isn't going to smush you? Well, the answer lies with the first thing that we talked about in relativity. It's the relativity of simultaneity. From your standpoint, the front and back doors closing, they were never closed at the same time. From your standpoint, uh, first uh, the back door closed, then opened, uh, so that the front end of the pole could go through, and then uh, the front door doesn't close until after the trailing end of the pole is through. So just to make sure that I've said that correctly, uh, from your vantage point, the back door of the barn closes first, then opens. The the front, the leading end of the pole passes through the back door. So the back door closes, opens, the leading edge of the pole passes through the back door. Shortly thereafter, the trailing end of the pole passes through the front door. Then the front door closes and then opens. From your vantage point, the two doors didn't close at the same time. The back door closed first, and then the front door closed after. But there was never a time where both doors were closed. They couldn't have, otherwise you would have been smushed, right? You have a 15-meter pole, and the barn, according to you, is only 6.6 meters. Hopefully that's all right. Let's look at invariance, because you're definitely going to need that to understand parts of this worksheet too. So a lot of the paradoxes in relativity are framed around those two that we just talked about. Maybe with a different story, um, but it's often built around um, either simultaneity being uh, something that it's hard to unlearn, and absolute simultaneity being difficult to unlearn, or uh, this idea of needing to uh, pick a frame that stays unaccelerated for the whole period. So this time, let's look at invariance. This is kind of helpful when comparing coordinates. There is this invariant, which is that c squared t squared minus the quantity of x squared plus y squared plus z squared is invariant across frames. So as long as the frames have as long as it's a special relativity problem where the neither frame accelerates with respect to the other, constant velocity between them, then c squared t squared minus the quantity x squared plus y squared plus z squared, end quantity, is going to equal c squared t prime squared minus the quantity of x prime squared plus y prime squared plus z prime squared, end quantity. I will just give you this equation. This comes from our Lorentz, right? So look at the Lorentz lecture. If right, t prime is just going to be this gamma times the quantity t minus vx over c squared. X prime is just gamma times quantity x minus vt, end quantity, and y prime is y and z prime is z. The nice thing about this is it will allow you to jump back. So these invariances, right, will allow you to jump back and forth between coordinates measured in one frame and coordinates measured in a different frame. The nice thing about these invariances, though, is they give us a way of relating events. So if delta s squared is equal to 0, we say that these are light-like. That, let me see if I can. So I've given green line a slope of 1, and I'm only plotting the x-axis, but our 4 coordinate axes here, the first 3 are spatial, the 4th is time. If delta s squared between between two events is 0, then we say that event A, which has coordinates 0, 0, 0, 0, and event B are light-like. This could be like sunlight leaves the surface of the sun and sunlight arrives at the Earth. If delta s squared is less than 0, we say that these are space-like events, and that event B could not be caused by event A. If delta s squared is greater than 0, we say that these are time-like, and it is possible that event B at coordinate x, y, z, and t was causally was caused by so causally related to caused by to event A that occurred at 0, 0, 0, 0. Hopefully that makes sense. It probably doesn't. Relativity is really mind-bending the first time you're exposed to it. So that is one of the nice things of these videos, is you can rewind it until stuff makes sense. Relativistic Doppler effect. Oops. Relativistic Doppler effect. The observed frequency compared to the emitted frequency is just related by this equation. I'm trying to keep under an hour, so I'll come back to that in lecture. But I just wanted to make sure that you had it for today. Relativistic linear momentum. So remember that we were using u as the variable for a speed measured of an object in my frame, and we were doing that because we had already used v to be the relative velocity between the primed and the unprimed frame. So the momentum is m naught u over square root of 1 minus u squared over c squared. We could write that as gamma u m naught u, where gamma u looks a lot like the other gamma that we were using, but note that this time it's not involving v, it's involving u. So the traditional gamma is for rectifying measurements between frames, right? But this gamma, um, if you're measuring an object, uh, you still need to apply this gamma u to make this relativistic momentum go, right? And so um, kind of the traditional one that you're probably remembering is that momentum is just mu. To relativistic, to turn this into a relativistic term, we need to add this gamma term. How come we never noticed it before? Well, again, most of the time u is going to be so small compared to c that u over c is basically going to be close to 0. Square it, it's really going to get close to 0. 1 minus close to 0 is basically 1. The square root of basically 1 is 1. 1 divided by 1 is 1. So note that this really does look a lot like our traditional description of momentum in everyday cases. We still have this Newton description that force is dp dt. And so let's look at this. So let's imagine that we have a force acting upon a charged particle. So it has charge q and mass m, and this charged particle is in an electric field, and that's producing this force. The magnitude of the force is just q times e. And so if we use the statement that force is dp dt, then qe is just going to be d dt of gamma sub u times mu. We can chain rule this, right? I am going to, so different books will take different approaches. The approach that we're going to take in this class is that m is invariant. There are books that will use a relativistic mass, and the relativistic mass is just equal to gamma u times m naught. I'm going to skip that approach. It's just we're going to just pick a lane. So it's also true that I'm more comfortable with this definition because it's the way that I was taught. So chain rule, we're taking m out, we're treating it as an invariant. But gamma sub u and u both have u dependence, obviously. And so you recognize this as just the chain rule of this. And so since we know what gamma u is, it's right here, we can differentiate that with respect to t. And we'll wind up with qe over m, I'm going to divide the m across, is quantity du dt times 1 over square root 1 minus u squared over c squared plus du dt times u squared over c squared times 1 over 1 minus u squared over c squared to the 3/2 end quantity. We can play some fancy games where I take this term and I multiply top and bottom by 1 minus u squared over c squared, and that turns the denominator into 1 minus u squared over c squared to the 3/2, which gives us common denominators. And so now I can factor out the du dt. Both terms have a du dt. Bring that out front. If I multiplied top and bottom of this term by 1 minus u squared over c squared, then the numerator of this becomes 1 minus u squared over c squared. And the numerator of this one is 1 times u squared over c squared, which is just u squared over c squared. And so 1 minus u squared over c squared uh, plus u squared over c squared is just 1. And so they have a common denominator, and you get 1 over 1 minus u squared over c squared to the 3 halves. That quantity times du dt. But remember that acceleration is defined to be du dt. And so I can replace this du dt with a, and then I can solve for the acceleration. So since we have the qe over m is equal to all this junk, we could, and this is a, right? We could solve for a, and it's just equal to qe over m times quantity 1 minus u squared over c squared and quantity to the 3 halves. But remember, starting at the beginning, we said that force was just qe in this problem, and so I could generalize this and say that the acceleration is oh, I think I just did something I'm going to greatly regret. Um, we won't do that again. Or maybe we will. Nope, we still didn't learn from our mistakes. Sorry, now it's just stubbornness, right? Okay. More generally, we could say that the acceleration is the force divided by the mass times quantity 1 minus u squared over c squared and quantity to the 3 halves. And we will pick up the rest of this in lecture so that I can keep this under an hour. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow. If the lab doesn't make sense, if the problems don't make sense, please don't hesitate to reach out to me. Thank you and have a good day.